So, now that we have ourselves calibrated here. So what did we go over last time? Last time we talked about the introduction to AC systems, or a review of AC systems, phasors, how to do basic calculations, linear system type calculations on an AC network, combining impedances together, essentially using KVL, KCL, Ohm's law, applying all the stuff that you're used to seeing in a DC system, but to an AC system. We went over a couple of examples. We'll continue doing that today. Like I said, for this very beginning portion of the class, I am going to expect you to be doing the phasor calculations by hand, meaning that you have to put it in polar form to multiply and rectangular form to add and subtract. Once we get past the first quiz, which I'll talk about today also, then we can start using calculators and make things a lot easier. But we'll also be moving on to a lot bigger and more complex problems, so it would be prohibitive to do it by hand anyway. We also talked about how power is represented in an AC system. Right, what we saw was that when we multiply the instantaneous voltage and current waveforms together, we end up with power, instantaneous power that has usually two different components to it, right? One is a component that's not time varying, and so that would represent the average power. And then we have a component that is time varying, and so the average for that is 0. That has a cosine omega t, or a sine, well, cosine omega t associated with it. That, what does that represent? What do we call that component of power? Does anybody remember? So let me begin by asking, the real power is the average. Right? The average we call the real power. So what was the other one?
Sine variant.
Okay, what was it?
Reactive?
Reactive. Okay, reactive power. And then together, they're called the apparent power. That's the letter S. And I often will refer to that as the complex power, just because it has complex components. Okay, and power factor correction, I think, was the last thing we talked about. We discussed first power factor. Power factor is the ratio between real power and the magnitude of apparent power. If power factor is equal to 1, that means that all of our apparent power is real. And what does that say about the phase of our voltage and current waveforms? They're in phase with one another. Okay? That's a good thing for a lot of reasons. One primary reason would be, yes? Losses, right, yeah. The current flowing along the lines, right, the I squared, so the current flowing along the lines and the loss associated with it, which is I squared R, right, is going to be calculated from the apparent power, not from the real power, right? I is equal to S over V, not P over V. And so, if we can reduce S and still keep the same amount of real power, usable power flowing through the lines, that's a good thing. What's one way we can do that? By eliminating Q. Okay? Q doesn't provide us any usable work. We get rid of it. We lower the magnitude of S. We can transmit the same amount of usable power to our loads, but we lower the magnitude of the currents as well as the loss. Okay, so moving on. It's like I have to go through the same process every morning. Projector doesn't work, check. Pen won't work with the iPad, then I turn it off, turn it back on. Okay. Now the pen will start working. Check. All right, I don't know what the heck's going on. All right, so, example 2.3. It asks us to find several different values. So, P, Q, S, and power factor for a circuit below, which I'll draw. So this circuit looks like this. We have, yep,
So P is instantaneous power, S is apparent power.
no. So P, I can do quick labels real quick. So this is power factor. This is apparent. This is the reactive. And this is the real. Now, if I asked for P of T, that would be instantaneous. And so that's normally the distinction there. If you see capital letters and you don't see the designation of time, then you assume that it's a phasor. Okay, so we have, I think it's the same, we're close to the same circuit we used in the last problem. Okay, so that's the circuit that we're looking for, or that we're dealing with, and our V1 is simply going to be 120 volts with an angle of 0 degrees. All right, so I think what we're going to do is, this is the same circuit as example 2.2, so we're not going to redo the work that we did for that one. So, example 2.2 tells us that the equivalent impedance for the entire branch, this whole thing here, it tells us that it's, does anybody have the number in their notes?
Yeah. 5.92 plus J 3.287.
5.92 plus J 3.87?
3.287.
3.287. All right, and if we convert this to a polar form,
6.78 with an angle of 29 degrees.
all right. And so we can go ahead and calculate the current, which we'll call I1, flowing through the circuit. I1 is equal to V1 divided by Z equivalent, which is 120 volts divided by 6.78 amps with an angle of negative 29 degrees.
Should you also find S by doing V squared over Z total?
Yeah. V squared over Z. Well, that would be equal. We don't know the power.
Yeah, like, would that be a way to find the power? Like rather than doing V times I, doing V squared over Z total?
Yeah. Yeah, you could. I think we'll need the current angle for finding the power factor and stuff like that. But you definitely could do it that way.
Alright.
Yeah, most definitely. Okay, so 120 divided by 6.78. In the calculator?
17.7.
And then I have 25 divided by square root of 2. Could someone divide that out? I don't know why I wrote that in there. Is that the same number?
Yeah, pretty much.
Okay. Well, we'll use 17.7. I don't know why I used that last time. Okay. All right. So,
Professor?
yeah.
Where's the negative 29 come from?
Well, because the angle 29 was on the denominator. So it's really, if you want to be, I'll stick a little 0 in there. So it's really 0 minus 29 degrees. Okay. So let's go through and calculate all the values we need. Okay, we can calculate. So first, what do we know? Let's state that for a second. Well, I don't need to write it down. What do we know? We know the current, we know the voltage, we know the equivalent impedance. We also know the power factor angle, right? And we know the power factor. I mean, we could calculate that very easily. Okay, so P. P is equal to the magnitude of V, magnitude of I, times the cosine of the power factor angle, which in this case is going to be what? What's the power factor angle? Is it? Positive 29 degrees, right? Because the power factor angle is equal to the angle of V minus the angle of I. And so what that gives us is 0 minus a negative 29, which gives us a positive 29 degrees. So the power factor angle is positive 29 degrees. So when we plug in our values, what we have is 120, we have 17.7, and then we have cosine of 29 degrees. And the value that I get for that is 1858 watts. Yep.
What does it mean for a voltage or a current to have an angle? I understand what it means for an impedance, but what is it relative to? You know,
Well, that's actually a very important question. So first, phase by itself is meaningless. It's a value that requires reference. Unlike for voltage, voltage has an absolute value because we have a universal reference, right? The ground potential is what we consider to be 0. So in an AC network, we need to set the zero crossing of one of the waveforms and say this is the 0 degrees for our system. More times than not, whatever the main voltage source is in the system, that will always be set. You'll notice that the angle for that will be 0 degrees, and that'll be the reference. And so you can see here, in this one, that's what we have here, is this is our reference with regard to phase. So everything is based off of, if you were to try to do these measurements using an oscilloscope and you're trying to calculate phase, you would be looking specifically at what is the difference in time between the zero crossing of these current or other voltage waveforms, because they're not all going to be 0, and the zero crossing of that. Okay, so then moving on, Q is going to be equal to magnitude of V, magnitude of I, sine of theta, V. So plugging in those values again, that will give us 1031 var. Okay. Now, one quick thing to keep in mind here is that we discussed this a little bit last time. Because phi is greater than 0, our system is what we call lagging. Okay, or our power factor is lagging. Right? We can have lagging, we can have leading. And lagging power factor is going to correspond to a positive value of Q. Leading power factor, meaning that the current waveform is in front of the voltage waveform. The power factor angle is negative. That's going to lead to a negative value of Q. Yeah?
Is there any benefit to having one lagging or leading?
Not particularly. Again, the goal in most of the things that we're going to be talking about is to get power factor to unity. So whether it's leading or whether it's lagging is not going to be of importance, except for the fact that it's going to change how we're going to do power factor correction, depending which direction we need to push.
That was basically my question.
So if you have leading power factor, that means you're going to have to use inductive elements as opposed to capacitive elements in order to push the system back in the direction. Okay, next. S is pretty straightforward because we have our P and our Q. So I don't think I even need to write out the numbers. I'm just going to say it's equal to P plus JQ. We know that. And then lastly, it asks us for the magnitude of our apparent power. And so that's going to be the square root of P squared plus Q squared, which then equals the magnitude of 1858 squared plus 1031 squared, which equals 2125 volt amps. I think that's it. Power factor, we got, well actually I don't think we've technically calculated it yet, so let's do that too. So power factor will be equal to P divided by the magnitude of S. So that would be 1858 divided by 2125. I don't have that in my notes. Somewhere about 90%.
87%.
Yeah.
Deese,
Mm-hmm.
could you also do the cosine of the angle, just to get power factor?
Yeah, you could just do cosine of the angle too. Yeah, exactly. Okay, so that's it for this example. Now we're going to move into the more meaty part of this, and that is the actual power factor correction.
Dr. Deese?
Yep.
Could you just talk about real quick how the units they go from var plus watts to volts amps?
So technically, are you talking about here? Talking about,
Yeah, when you're calculating the S.
yeah, the S. So technically, volt amp is an all-inclusive unit above all the others. Because when you calculate watts, okay, it's really, because using SI units, right, you can break it down and call it anything you want as long as the units work. So the definition of watts is volts times amps. The definition of var is volts times amps. So they're all volts times amps. So that's, I mean, it's just a more generic way of saying it. So you could call any of those volts times amps because they're composed using Ohm's law, right? Volts, or not Ohm's law, but P equals VI, so volts times amps.
So just sort of like a naming convention to make things sort of like obvious that when you see var, you'd know you're definitely talking about like reactive power.
Yeah, that's all it means. Volt amp's reactive. You could say volt amps. You could say volt amps for all of it.
Well, and isn't reactive power 0 watts, right? Wattless.
Well, yeah, I mean, watt is a unit that's reserved for real power. That's the definition of it. It's used to describe it there. I mean, look, like most units, right, we don't really need any units in engineering or science besides like second, meter, right? You can make everything in conjunction with, acceleration and all the other stuff. Force becomes power, becomes energy. So, all of these are just renaming of what already we have. And that's what's happening here. If you want it to be very dry about it, just go call everything volt amps, all of it's volt amps, and it makes sense as a, some guy, well, not some guy, James Watt's not some guy. But anyway, they named a unit after him. So we call it watts, but you mean it's there's different names for the same thing, I guess is what I'm saying. But in the end, they're all volt amps, so the units do agree. Okay, so power factor correction. Okay, so the question we're going to ask ourselves now is, how do we perform power factor correction? How do we take a system like what was in example 2.3 and change it such that the power being consumed from the first source, the V1, has unity power factor. So in order to do that, what we're going to do, okay, is we are going to place a compensating element in parallel to our target to nullify the reactive power drain or injection. So place a parallel component or a compensating element, in parallel with our target to nullify or offset, another way is to say that, the reactive power draw or injection. Okay. So an important thing to pull out of here is the use of this word target. So power factor correction can be performed in multiple ways for the same system. Or I could even say multiple times for the same system.
You always do it in parallel though?
Well, we'll talk about that in a second. If you go back up to this system we have right here, if our goal is to perform power factor correction and our target is the generator or the source, then we would need to place a parallel element right here. Okay? However, if our goal was to perform power factor correction for the load, then we would put an element right here. So that's going to be an important part of the question, is also what is our target for the power factor correction. Now, why do we put it in parallel as opposed to series? That is sort of a practical question. Let's say, well, as opposed to trying to give some sort of analogy, I think I'll just draw it. So you have a certain amount of Q that's flowing down this branch right here, okay? If you want to nullify that Q, placing something in series is not really going to help, right? Because a series element is not going to allow, right, we have the current flow along, KCL dictates that the current flow along that line is not going to change, okay? So a series element is not going to allow a reversal of the direction of the Q. By placing an element here, with the same voltage, it'll have the same voltage across it. We can design it such that the Q flows in the opposite direction, right? If one's an inductor and the other's a capacitor, or vice versa. Then, if we size them properly, we can get it such that the two Qs, the Q1 and the Q2, sum to 0. Which means that, from the point of view of right here, when you're looking at the load or scoping the load, looping the power factor correction element in with the load, the power factor will be 1. In essence, placing a series element wouldn't allow us to inject or consume reactive power directly from the node, like how we need to do it. Okay, so if we draw a little picture here, we have, let's say, a line element. And then we have a load. We would place our power factor correction or our compensating component here. Assuming that this is the target. So therefore, what we have is we'll have a value of QL that'll be consumed. We'll have a value of QPFC that is being injected. And then we'll have a value of Q transmission line, which will be equal to QL minus QPFC, which could be equal to 0 if we design everything correctly, right? Obviously, the sizing needs to be done right. So the main task Our main task is going to be properly defining whatever the value of ZPFC is, the compensating element. All right, so now let's try example 2.5, and that's going to give us our first crack at actually performing power factor correction.
Dr. Deese, you mind if I crack the door?
Yeah, go for it. So calculate the power factor correction element to affect unit power factor. There's two ways of saying the second part. With V1 as the target, or you may see the book say as seen from V1. Okay, as observed from V1. If you were scoping or examining how much power is being injected, it wouldn't be consumed, but, well, I guess it could be consumed, but let's say injected by this source. From that point of view would be that which we would see Q equals 0. Okay, so let's draw our system real quick. Okay, so a couple things here. We assume that the compensating element is capacitive because the load is inductive. And we know that power factor will initially, before we perform our power factor correction, lag.
So the capacitance is what you added on?
Yeah, this is the piece we added on. So the original system was just this.